So with the Tower of Hanoi puzzle, you may be thinking, okay, so it takes 2 to the n minus 1 steps to solve the puzzle if you have n disks. Well, is it a lot? Is it few? Is it going to take forever? Or is it going to be easy? And how do we even talk about it? So generally, we will talk about function growth, because here you're not really interested in what happens when n equals 8. You're kind of interested in how much harder, how much longer would it take to solve the problem if you increase n by 1, or just generally if you keep increasing n. So let's see. So for that, we need a concept of the function growth, the rate of growth of a function. So what does it mean that a function grows at a certain rate? We could talk about one function being larger than another. Well, how do we do that? Is 100 times n larger than n squared? Well, depends what your value of n is. When n is less than 100, then 100n is larger. But if n is equal or bigger than 100, then n squared is larger. So there are only relatively few places, 100 places, where f of n is larger, and for the rest, infinitely many places, g of n is larger. So intuitively, g of n is kind of bigger than f of n, in the sense that it grows faster than f of n. So to compare functions, which one's bigger, which one's smaller, which we do a lot in computer science, because we often need to compare the running time of different algorithms, performance of different structures. We need to look at what happens when n, which in computer science tend to be the size of the input, increases. Because really, if you have a problem with only very few things in the input, if you just got 1 or 2 disks, it doesn't take too long to solve the puzzle. So you don't really care if there is an extra step. But, you know, the larger n becomes, the longer it takes to solve the problem. So the more you care how long it actually takes. And mostly how much longer it takes with every extra piece, every extra disk. So we want to compare the growth rate of the functions. How would we do it? How would we estimate how a function grows, and more generally, how would we look at several functions and say this one grows faster, this one grows slower, those two are kind of the same? The first thing that you may think about is plotting a graph of a function, as we've probably done before. So let's try it with a few common functions. So here are functions of log n, n, 2n, n log n, n squared, n cubed, and 2 to the n. The green one is n cubed, and if you look at it, you say, okay, so looking at this picture, surely n cubed is by far the fastest growing function, right? Well, let's look a little bit further. The first graph was for values of functions from 1 to 2. The second graph is for values of function from 1 to 11. And you could see how 2 to the n, which wasn't really doing much between 1 and 2, by 10 overtaken the n cube, and it seems like it will keep going and going. So which one of this group grows fastest? So far, 2 to the n seems like the likely candidate. And well, indeed, in this group of functions, it will be 2 to the n. But who knows, maybe in a different group of functions, if we only plot up to 10, then some other function will dominate. or maybe there is a function that grows faster than 2 to the n in a group, but we cannot see it if we only plot up to 10, which brings up the question, maybe we need to plot up to 20, 200, 2000. What is the number? Or maybe you could get away from plotting altogether and compare the functions differently. So I would say that plotting is not conclusive because so far I haven't seen a proof that plotting something up to any specific number is going to tell you for sure what happens as n goes to infinity. And in fact, it's possible to construct counterexamples for any possible number up to which you grow your functions. So what else can we do? So here we introduce a concept that you're going to see over and over and over again in your algorithm courses. Well, pretty much any course in which you need to design, in which you need to solve computational problems and do it efficiently. So first, let's go and define the function growth again. So we would say that f of n grows at most as fast as g if there is a value of n, and here n is just a natural number, such that after n0, that is for value of n that are greater than n0, f of n is at most as large as g of n. And we will relax it a little bit too, because really, if the only difference between two functions is a constant factor, it doesn't really affect their growth rate, even though 2n will be larger than n, but kind of similar. And there is a computer science reason why we want to ignore constant factors too. Oftentimes, you try to compare performance of different algorithms, but one of them is implemented in C and running on a Mac, and then another one is implemented in Python and running on a Unix server. Well, how do you know how to compare the algorithm, given that the time will be fairly different? Well, it will be different, but in fact it will be different by a constant factor. So we really want to throw the constant away in order to be able to do a fair comparison. And this is what's achieved by using the so-called big O notation. So we say that the function f is in big O of a function g, or some books will say is big O of a function g, it depends, if basically from some point on, some number n0, there will be, well, basically if the function g grows as fast or faster than the function f. And we say that g is the upper bound for f, because if you look at it in a graph, eventually g becomes above f, and asymptotic upper bound because it becomes above f as n goes to infinity. And moreover, sometimes we want to say that the function has the same growth rate, and in this case it means that f is in big O of g and g is in big O of f, and then we write O with this line in the middle, which makes it a Greek letter theta. So f is big theta of g if they have the same growth rate. So if you want to see a general definition, when we are not talking about functions of natural numbers, but talking about function of reals, here it is. So here instead of n, I'm writing x, because n is usually a natural number, x is anything, like a real number. So there is a number x and a constant c which is greater than 0, and the x is also greater than or equal to 0, such that for all x that are bigger than that x0, the absolute value of the function f is less than constant times absolute value of the function g. And again, it means the same thing. From some point on, f, in this case absolute value, is no more than g times a constant. So this is a general definition, which you're not going to see again, because in computer science we tend to talk about big O notation mainly when we talk about running times of programs, number of steps a program takes, and number of steps is a natural number. It's positive and it's an integer. So we're never going to need the absolute values, and we can just use n natural number and not think about reals. So here we will introduce big O notation and show some example, but you will see a lot more of it in your algorithm course in COMP1002, and chances are you will see it in many other computer science courses, starting with COMP1000 and COMP1001. Whenever you talk about efficiency, whenever you talk about performance of programs, chances are you talk about it using the big O notation. So let's do a few examples. Here is a formula defining what it means for f to be in the big O of g. And here I changed x's to n's, talking about natural numbers, and got rid of the absolute values, because this is where you're probably going to see the big O notation, at least in computer science. So let's start with f being n squared and g being 2 to the n. And you might have come across it when you were doing exercises for induction. With the base case n equals 4, you could show that 2 to the n grows faster than n squared after 4. And what that means is that f of n will be less than or equal g of n, and in this case we didn't even need c. C was 1. We just said f of n is less than or equal, well, 1 times g of n. So that proved to us that n squared is indeed in big O of 2 to the n, and 2 to the n grows faster than n squared. So now let's keep f n squared, but now let g be 10n. What happens then? So take any c that you like. So no matter what that c is, look at what happens when n is greater than c times 10. Well, then n squared will be greater than c times 10n. So there is no way to find a c n and then 0 such that after that n0, n squared would be less than c times 10n. And that tells us that n squared is not in big O of 10n. By the way, you probably noticed that here, rather than calling functions f and g, when I'm doing the big O notation, I'm just writing n squared and 10n for the names of the functions. So let's try something else. So now let f be n squared plus 100n, and let g be 10 times n squared. Okay, now it's a bit of a race. We got 100 in the first one, and we got 10 times n squared in the second one. So which one grows faster? The interesting thing here is that they actually have the same growth rate. So we will show that f is not just in big O of G, it's in theta, big theta of G. So first, for that, we need to show that f is in big O of G, and we could take, for example, C equals 20. 20 times 10 is 200. That's enough for G times 20 to be bigger than f. And also, if we take n0, maybe even c equals 1, but n0 equals 100, you will see that the first function becomes kind of 2 times n squared at this point when n equals 100, when g is 10 times n squared. And after that, we already know that constant times n grows slower than n squared. So from that moment on, g, the n squared, so you could think of g as n squared plus 9n squared. And you could think of f as n squared plus 100n. And all is left is to say that 9n squared grows faster than 100n. So now, why is g in big O of f? How can we do it the other way? Well, you know, if you multiply f by 10, we get the leading term 10n squared, which is already same as g, and then we are also adding something to it, which is positive number, 100n. We get something bigger than g, no matter what n is. So we can start with n0 equals 1. So one thing to get out of it, other than constant don't matter, is that if you have a sum of different functions, you could essentially throw out all of them except for the fastest growing function and strip the constant in front of the fastest growing function, and that kind of tells you the growth rate of your function. And a lot of time when you will see big O notation used, it will not be something in big O of complicated long summation with constant. It will be in big O of, you know, n square, n cube, or maybe n times log n, because you cannot, log n kind of has a growth rate smaller than n but bigger than constant, so we cannot really ignore it. But in general, the rule of thumb, when you're doing the big O, just look at the highest growing term in a sum, throw everything out, and throw the constant, and that gives you an answer. So in particular, a lot of time when people talk about complexity of algorithm in particular, they will talk about classes corresponding to big O of such kind of simple functions without additional things added and without constant. So for example, one such class is linear big O of n. Those are functions that are in big O of n. And by the way, some of them can be faster, but generally, especially when you're talking about solving a problem, you just care that there is a way to solve it in time big O of n. Faster is better, but big O of n is good enough. So here are the classes. So logarithmic when it's big O of log n. Occasionally there is big O of log squared n or big O of log n, but log n is probably more common. Some of the common search algorithms are big O of log n complexity. Linear big O of n. Big O of n log n, I don't know of a common name for it, but you see it a lot, especially in your COMP1002. You're going to see it in a lot of places. in sorting and graph algorithm, in all sorts of places, and log n just seems to come up a lot. Then we get into polynomial functions, such as quadratic, cubic, and in general n to some constant. And usually the general agreement is that you could solve the problem fast if you could solve it, and I'll say in a moment what I mean by solve it, in time which is a polynomial. And then we have exponential, which is a big O of 2 to the n. By the way, so I keep talking about ignoring constant, but the only place where you can really ignore constant is in front, all the way in front of the function, which is of which you're doing the big O. Because if you look at 2 to the 2n, the 2 on top you cannot really ignore, because that's not really a 2, that's a square. So 2 to the 2n is 2 to the n squared, and you probably already figured that you cannot ignore a square. So even though ignoring constant is a rule of thumb, make sure you know where the constants are before you ignore them. So in general, there is a whole method, there is a whole chapter in your textbook about solving recurrences, and it can be tricky, but luckily a lot of recurrences that you will see in your algorithm course, recurrences that come out of writing recursive programs and figuring out how long they take to run, have a very special form. And with that form, you could figure out the growth rate of a function that this recurrent define and the time it takes for a program to run by using so-called master theorem. So I'll skip it for now, but just to let you know that there is a general method of solving very general common types of recurrences coming out of recursive algorithms. So now that I keep alluding to programs and algorithms and performance, let me actually say what I suppose you have a computational problem that is just some kind of problem where you have some inputs and you want to get their solutions or outputs. For example, you have a number and you want to compute its factorial, or you have a list of elements in the array and you want to find whether the element, well, and you want to output the array of the elements in the sorted order. Lots and lots and lots of things are computational problems, and most often you will write programs to solve those computational problems. I mean, not always, like Hello World doesn't really compute much, but a lot of time you'll have an input, and for every input you'll have to compute a solution. And in this case, it makes sense to talk about how fast you could get a solution from an input. Usually when inputs are small, getting a solution is pretty fast, but as inputs become longer and longer and longer, it takes longer to find a solution. Again, if your input is a list of numbers, and say you need to check whether the list contains a specific number, well, the longer the list, the longer it may take you to find the number. So what does it have to do with growth of functions? Well, suppose you do have an algorithm, a method that for every input x solves the problem in number of steps, which is some functions of the length of the input. And moreover, suppose that this t, which tells us the number of steps, is in big O of some function. That's great, because then you could say the problem is solvable in time f. And usually t may be a very complicated formula, but f can be, quadratic, linear, cubic, one of the easier to describe, easier to say function that we listed a couple of slides ago. You may say, wait a moment, but maybe I have several different methods of solving problems. That's great. You just pick the best one, and that will tell you the upper bound on the time it takes to solve the problem. If you could do something in time n, then in particular, you could do it in time at most 10 squared. You may be wondering why I'm suddenly talking about algorithms and number of steps, even though I kind of mean the running time and performance. Again, the reason is I don't want to care what is the machine on which the program is running, how it was implemented, how many other things are running on the machine at the same time. Lots and lots of things can affect the actual time it takes to process. But the number of steps is something much more tangible, much easier to deal with. So as an example, we had a way of solving the Tower of Hanoi puzzle, which had 2 to the n minus 1 steps to move n disks. So we could say that the complexity of solving Tower of Hanoi is big O of 2 to the n. And sometimes, that doesn't happen that often, but sometimes we could also prove that some function f is the best we can do. If we know that the complexity of solving problem is in big O of some function f, and we cannot do any better, then we could say that the problem has complexity big theta of f, and then we pinpointed the complexity of a problem. We can do it for Towers of Hanoi, at least with 3 pegs. We know that any algorithm needs 2 to the n minus 1 steps, and we know that there is algorithm that takes that many steps. So we know that complexity of solving Tower of Hanoi is exactly theta of 2 to the n. So need 2 to the n, and 2 to the n is enough. But problems for which we could prove it are not that common, and there is a whole field, computational complexity, which is working on understanding what makes some problems hard and trying to figure out whether there is an algorithm that can solve something faster or there is no such algorithm. And again, it goes back to very beginning of our class when we talked about the $1 million problem. That's exactly the $1 million problem again. Can you show that there is no algorithms that solves, for example, given a formula, if that formula is satisfiable, problem in time faster than, say, big theta of 2 to the n, like truth tables? If you solve that one, remember you get $1 million, but remember it's not the easiest way to get the $1 million, so maybe one of you can get it. So anyway, so to prove an upper bound on complexity of a problem, it's enough to find one algorithm that solves it in some time which is in big O of f. Then f is an upper bound, you're done finding an upper bound. Can you find an upper bound that will be smaller? Can you do it faster? Well, that's a whole different question. If you can find an algorithm that's better than the one you had, great. But suppose you're trying to find an algorithm and you can't seem to find it. Well, it could be that there is a lower bound, which may or may not be the same as your upper bound. Well, at least you may not be able to prove that it's the same, but you might be able to prove a lower bound on the complexity of a problem by showing that no matter which algorithm you take, it has to have at least t of n steps. which is so it has to have at least f of n steps, which means that f of n is in big O of t of n. So here we've reversed. Before we were talking about t of n being in big O of f of n, and now it's f which is in big O of t. And if this happens and we still want to talk about something f of n, there is a notation called big omega, the Greek letter omega, where you could say t is in big omega of f, meaning that f is in big O of t. So if you can show, like with Tower of Hanoi, that any algorithm needs at least some function of steps, then you would have shown the lower bound, the big omega. So the Tower of Hanoi is in big omega of 2 to the n.